isothermal change, P1V1 equal to P2V2, that is PV equal to constant. An adiabatic process in which there is no exchange of heat between the system and its surroundings. That bomb colorimeter has been sealed, so the volume changes cannot be observed, volume does not changes only. Therefore, the decrease in internal energy must result in a decrease in the temperature of the gas. Hello everyone, this is Harshita Bhavasar from Vidhyaashram School of Excellence. Today we are starting up session 4 from the chapter Thermodynamics. In the last class we have discussed about first law of thermodynamics and about enthalpy. In this session we will discuss about relationship between P, T and V, that is pressure, temperature and volume for an adiabatic process for an ideal gas, and measurement of delta U and delta H, that is internal energy and enthalpy. How can it be measured? We will see in this session. And some of the extra information also could be seen in this session and can be used for your competitive examinations. Relationship between P, T and V for an adiabatic process for an ideal gas, that is pressure, temperature and volume in the adiabatic process for an ideal gas. For an isothermal change, P1V1 equal to P2V2, that is PV equal to constant, means pressure and volume. With the two systems, if we keep on comparing, pressure and volume is constant. For an adiabatic process, the following generalizations can be derived. Adiabatic means no heat can be exchanged between system and surrounding. Between the process, that will be called as adiabatic. See here, P1V2 equal to P2V2 equal to PV equal to constant. This is a gamma constant they have written, where gamma is the ratio of heat capacities. It is the ratio of heat capacities, that is Cpy by Cv. These are the heat capacities. So, it is the ratio will be called as that gamma. T1 by T2 equal to V2 by V1. It is inverse, right? That is why gamma minus 1, or T into V equals gamma minus 1 equal to constant. Here T2 by T1 equal to P1 by P2. It is in mixed fraction. They have given gamma by 1 minus 1, or TV equal to 1 minus gamma by gamma equal to constant. An adiabatic process in which there is no exchange of heat between the system and its surroundings. This is the adiabatic process where no heat will be exchanged between system and surrounding. Heat can neither enter nor leave the system. Within the system, heat cannot be entered or cannot leave from the system. So, Q equal to 0. The first law equation, internal energy equal to Q plus W, that is heat plus work done becomes delta U equal to 0 plus W. Because Q will be equal to 0, so 0 plus W. In such a case, positive work is done by the gas during expansion, and so delta U will be negative, because positive work done by the gas during expansion, that is system is getting to expanded by the gas, and so work will be done by negative by the system, right? That is why, and internal energy will be negative. This indicates that the internal energy of the final state will be less than that of the initial state. Whatever the internal energy present in the system at the final stage will be more than the initial stage. This means that work of a adiabatic expansion comes only from the internal energy of the gas. Means what, by these statements what we have understood? The work of adiabatic expansion, whatever the expansion of by the system or by the gas is being done, it comes from the internal energy of the gas. Therefore, the decrease in internal energy must result in a decrease in the temperature of the gas. If the internal energy of the system is getting decreased, obviously the temperature of the gas will decrease, because the work of adiabatic expansion will be done by the internal energy of the gas, by isothermal and by adiabatic. See here, it is in the initial state getting to final and getting expanded, and this is isothermal. See here delta V, isothermally it has been expanded, here pressure, here volume. Okay. Next, comparison of volume changes on expansion. Pressure versus volume relations for isothermal and adiabatic changes are shown in the figure. This is the graph overall they have shown. Since gamma is greater than unity, for the same initial pressure and volume, an adiabatic expansion to identical final volumes will result in a lower final pressure than the final pressure of the isothermal process, since adiabatically expanded gas gets cooled during the process. Why they have shown here very much low in initial or final than the isothermal means expanded gas gets cooled during the process. Also, for a given decrease in pressure, an adiabatic expansion would be accompanied by a smaller volume increase than that in an isothermal processes from the initial state. Next, this is to be expected since the temperature decreases in the adiabatic process. This is the reason why the temperature getting decreased in the adiabatic pressure. Next, measurement of internal energy and enthalpy by using calorimetry. We can measure energy changes associated with the chemical or physical processes by an experimental technique called calorimetry. Means chemical and physical changes, we can measure those changes by using calorimetry. In calorimetry, the process is carried out in a vessel called calorimeter, which is immersed in a known volume of a liquid. That overall vessel called calorimeter will be immersed in a known volume of liquid. Knowing that heat capacity of the liquid in which calorimeter is immersed and the heat capacity of calorimeter, it is possible to determine heat evolved in the process by measuring the temperature changes. Measurements are made under two different conditions. Means the knowing by heat capacity of the liquid whichever that calorimeter has been immersed, and it is possible to determine heat evolved in the process by measuring temperature also. But two different conditions are constant volume and constant pressure. By getting these two conditions, that heat capacity of the liquid can be known and the measuring temperature can also be known. See here, first we are seeing that internal energy measurement. For chemical reactions, heat absorbed at constant volume is measured in a bomb calorimeter. For internal energy, they need bomb calorimeter. Here, a steel vessel is immersed in a water bath. The steel vessel will be considered as the bomb. It is immersed in a water bath. The whole device is called calorimeter. The steel vessel is immersed in water bath to ensure that no heat is lost to the surrounding. The heat vessel, how it should be present and which is immersed in the liquid, that heat cannot be lost to the surrounding. Okay, this is calorimeter, this is water, it is immersed here, this is bomb calorimeter. Okay, whatever the heat is present inside the calorimeter, it should not lost to the surrounding. A combustible substance is burnt in pure dioxygen supplied bomb calorimeter in the steel bomb. See, the burnt pure dioxygen should be supplied. Heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. Whatever the heat evolved during the reaction, it should transfer to the water in which that bomb calorimeter is being immersed and that temperature should be monitored. Since the bomb calorimeter is sealed, its volume does not change. The energy changes associated with the reactions are measured at constant volume. That bomb calorimeter has been sealed, so the volume changes cannot be observed. Volume does not changes only, but only the energy will be changed. That has to be measured. Means at the constant volume the energy will be measured. Under these conditions, no work is done as the reaction is carried out at a constant volume in the bomb calorimeter. Since the bomb calorimeter has been sealed, only the energy exchange is taking place. No work is done in the calorimeter. Even for reactions involving gases, there is no work done as delta V equal to 0. Since that constant volume is present inside the bomb calorimeter, in the gases or liquids, whatever the state of matter, heat or overall work cannot be changed. Temperature change of the calorimeter produced by the complete reaction is then converted to QV by using known heat capacity of the calorimeter. But temperature has been changed, that should be converted into QV and heat capacity of the calorimeter. That next one is enthalpy measurement. Measurement of the heat change at constant pressure. Enthalpy is nothing but heat energy that will be at constant temperature. We know that delta H equal to QP at constant pressure, and therefore heat absorbed or evolved at constant pressure is called heat of reaction or enthalpy of reaction. In an exothermic reaction, heat is evolved. In an exothermic reaction, heat will be evolved. Exo means outside, therm means heat. That heat will be evolved to the outside and system loses the heat to the surrounding. From the system, the heat will be liberated to surrounding, means system will lose the some of the heat. QP will be negative, yes, and enthalpy will also be negative. Similarly, in an endothermic, endo means inside, therm means heat, the heat which is absorbed by the surrounding to system, heat is absorbed, QP is positive and delta H will be also positive. This is calorimeter for measuring heat changes at constant pressure. This is also a calorimeter. This is reaction mixture, whatever inside, and formed polystyrene cup. This is a thermometer to measure how heat will be evolved or absorbed. Next, some of the problems. A sample of gas changes in volume from 4 liter to 6 liter against an external pressure of 1.50 atmosphere and simultaneously absorbs 1000 joules of heat. The change in internal energy of the system is. There are 4 options. Work of expansion, work equal to minus P external into delta V. Means it has been expanded, that is why negative. Minus 1.50 atmospheric pressure, that is 6 liter to 4 liter equal to 3 liter atmosphere, and 3 into 101.3 equal to 1 liter atmospheric equal to 101.3 into 3 means minus 304 joule will happen. Change in internal energy, delta U equal to Q plus W, this is first law of thermodynamics, 1000 joule minus 304 joule means 696 joule will become, that means C option will be the answer. Next, a gas expands isothermally against a constant external pressure of 1 atmosphere from a volume 10 dm cube volume of 20 dm cube. It absorbs 800 joules of thermal energy from its surroundings. Delta U for the process. It is again work expansion minus P external, V final to V initial, minus 1, 20 to 10, 10 liter atmospheric, 1 liter equal to 101.33 joule, means overall minus 1013 joules. Heat absorbed means plus will become 800 joule. Delta U equal to Q plus W, because heat absorbed by the system, that is why plus 800 minus 1013 equal to minus 213 joule, that is answer C. Here the sign conventions we have to work absorbed, heat absorbed means positive, heat liberated means negative. A certain amount of zinc is dissolved in HCl at 25 degrees Celsius in an open vessel. The type of process and the work done by the system respectively is isothermal positive, isobaric negative, isochoric 0, isothermal 0. In an open vessel, okay, at the 25 degree Celsius HCl has been present and zinc is dissolved in it. The type of process and the work done by the system. When HCl reacts with zinc hydrogen, gas is liberated at constant pressure. Hence it is isobaric process. The gas expands against external pressure, so that work done by the gas is which is negative, means isobaric and negative. The reversible expansion of ideal gas under adiabatic and isothermal conditions is shown in the figure. This is adiabatic, this is isothermal, pressure versus volume, P1, V2, V3, this is P2, V2, T2, this is P1, V1, T1. See here, which are correct? A, C and D is correct. T1 equal to T2, correct? T1 equal to T2 and W iso is greater than W idea. This is also correct. And D, delta internal energy of iso is greater than adiabatic, that is adiabatic process. This is also shown in this picture. See here, for that explanation T1 equal to T2 because the process is isothermal. Here temperature is completely constant. Work done in adiabatic process is less than isothermal process because area covered by isothermal curve is more than the area covered by the adiabatic curve. By seeing curve only we can understand. In adiabatic process, expansion occurs by using internal energy, hence internal energy decreases. On the other hand, isothermal processes temperature remain constant and no heat change in delta H. These are the common points we have understood from the previous session. If we implement in the problems, they will give by the tricky questions. By implementing, we have to analyze, or else every problem will be in a difficulty manner itself. These are the additional information. This is Joule-Thomson effect. When a gas at high temperature is allowed to expand to a low pressure region through a porous plug adiabatically, the expanded gas undergoes a cooling effect. This is known as Joule-Thomson effect. Means from a high pressure to lower pressure. From a high pressure to lower pressure, there what gas is expanding means through a porous plug adiabatically. That gas will undergo a cooling effect. Correct? That effect will be called as Joule-Thomson effect. In Joule-Thomson expansion, enthalpy of the system does not change. In other words, the process is not only adiabatic but also isoenthalpic. Proof of being in the isoenthalpic is given. See here, from high to low through porous wall, exhibit C cooling effect, and that effect will be called as Joule-Thomson effect. These are all insulated wall. In Joule-Thomson expansion, cooling effect occurs because the energy which is required to overcome the attraction between molecules during expansion is consumed by the internal energy, that is kinetic energy of the gas molecules after expansion is lower and such temperature falls. Due to the kinetic energy, the movement of molecules, so the cooling effect will start. That is how from the higher pressure to lower pressure, that temperature will falls. The phenomenon of change temperature produced when a gas is made to expand adiabatically from a region of high pressure to a region of extremely low pressure is called Joule-Thomson effect. That we have understood already. Next one is inversion temperature, that is Ti. It is observed that greater the pressure difference, greater will be the decrease in temperature. If the pressure difference is more, means that collision between the molecules will be low, automatically temperature will get less. Lesser the initial temperature, greater will be the decrease in temperature. Yes, initially only the temperature is low, means finally obviously it will low. As the initial temperature is increased, the cooling effect decreases. At a particular temperature, neither cooling nor heating takes place after expansion. This temperature is known as inversion temperature. Means after, at a particular temperature, neither cooling nor heat will takes place. After expansion, that expansion period will call it as inversion temperature. Above this temperature, warming effect takes place instead of cooling effect. Inversion temperature, that is Ti, is given by an 2A by Rb, where A and B will be the van der Waal constants. Next, Joule-Thomson coefficient. Joule-Thomson coefficient is defined as the rate of change of temperature within the pressure at constant enthalpy condition. This is constant enthalpy. Temperature and pressure will be seen here. This is Joule-Thomson coefficient. In other words, Joule-Thomson coefficient is the rate of change of temperature with the pressure in a streaming process through a porous plug. Joule-Thomson coefficient is directly measured from the temperature change at delta T of the gas as it undergoes a pressure drop delta P through a porous plug. We have seen that Joule-Thomson effect in that porous plug will be seen. The temperature and pressure constants we have seen. By that, at the constant enthalpy, that coefficient will be considered here. Joule-Thomson coefficient is 0 for an ideal gas because in an ideal gas, van der Waals of intermolecular attraction are negligible and there is no consumption of energy in overcoming them. Already van der Waals constant are present, overcoming energy is not seen in intermolecular attraction. Hence, the temperature of ideal gas remains unchanged by Joule-Thomson expansion. However, real gases have non-zero Joule-Thomson coefficient. Sign of mu Jt may be either positive or negative. This coefficient may be positive or negative. If it is positive, it will be coefficient will be greater than 0. Delta T, that is temperature, becomes negative. Cooling takes place on expansion. Whenever the expansion will take place, interaction of molecules will also increase. Delta T will become negative. If the coefficient is negative, means lesser than 0, delta T becomes positive. Warming effect takes place on expansion. Next, degrees of freedom. The number of coordinates required to locate all mass points, that is atoms, in a molecule called number of degrees of freedom. A molecule has 3n degrees of freedom where n is the number of atoms present in it. In a molecule, there are so many number of atoms. Based on the number of atoms present in it, we will give the degree of freedom. A molecule have translational, rotational and vibrational degrees of freedom. A molecule will feel or exhibit 3 kinds of degrees of freedom, that is translational, rotational and vibrational. This is the extra information, that is Joule-Thomson effect, inversion temperature and whatever the degrees of freedom you will see in your next classes. But I have given the extra information. But that enthalpy and the relationship between pressure, temperature and volume in an adiabatic process is very much important. So, we will see in the next class. Topics are principle of equipartition of energy and thermochemistry will be discussed in next session. Whatever I have done in this session, I hope you have understood. So, we will meet in the next session. Thank you.